Hello, my name is Neo Ra, and this is my lab video report for Lab 3 on black hole and orbits. This is what the video will cover, starting from introduction, and it has two parts, part 1 black hole and part 2 orbit, and all the way to conclusion. The purpose of this experiment is to use GlowScript's computational model to predict the motion of objects in space affected by gravity. Here are the related concepts and used formulas for this experiment. Newton's second law states that the net force is mass divided by acceleration. Basically, force needed to speed up or down an object is proportional to its mass. And when the net force is zero, the acceleration also becomes zero. And circular motion is a formula used to predict the motion of an object that is going in a circular orbit. You can see that the F net, the net force, is divided into parallel force and perpendicular force. Here is the preview of the result of the experiment. You can see that both the black hole orbit and the spaceship orbit has been well represented by the computational model. Now we will jump into the actual experiment. First part was the experiment of recreating a computational model of a star going around a black hole with gravity. The system, obviously, would be star, and the surroundings would be the black hole exerting gravity on each other. Here are the initial conditions of the experiment. I used the seed, as you can see on the top right corner for my email, and the gravity constant, the mass of the star, which is 2.0 times 10 to the 30th power, and delta T, which is 60 times 60 times 24, which would account to 1 day in seconds. And as you can see on the screen, the formulas to calculate the initial velocity all the way to F net perpendicular are shown on the left side of the screen. And the right side was a code that I used to calculate the mass of the black hole. Here is the result of the first experiment. The result, mass of black hole, was 2.01089685314,685 and 10 times to the 34th power kilograms. What does it mean? The net force, obviously, is the sum of all the forces the star is under effect of, which means the only thing, the gravity by the black hole. The rate of change of momentum of the stars is the actual change in star's motion, and parallel affects the star's speed and perpendicular star's direction. Part 2. This is the simulation of a spaceship under the effect of gravity of a star and the planet, and it trying to represent a 8 motion. The system would be the spaceship, and the surroundings would be the star and the planet. The initial conditions are shown like this. The same formulas were used for the velocity and gravitational effect on the spaceship as part 1, so that's shown on the right side of the screen. And on the left side, you can see the initial speed that I used through trial and failure, and it is x and y each 24,200. The result, it did not represent a perfect 8 motion, but it did not crash into the moon, and it stayed within the system, which would be a success. Discussion. What would be the possible sources of error? It could be the forces that were neglected because this was a very limited computational representation, and it might have been because of the incorrect initial velocity in part 2, lab 2, not lab 2, part 2, and it might have been because of the mistyped formulas. What if? If we combine part 1 and 2 and include all objects, the star, black hole, planet, and spaceship, we would need to put into account the gravity between each object. The spaceship would be the smallest mass, which is affected very largely by others but exert little effect. The black hole with the largest mass, affected very little by others, exert great effect. Conclusion: succeeded in finding the mass of the black hole, successfully created orbit of the spaceship around the moon.